So it's been known for some time that the amount of sleep that you have influences how much weight you maintain. And it's hard to do experiments with people on this because we don't really want to interrupt people's sleep and have them get less sleep or more sleep, et cetera. So they did an experiment on mice. They had 18 different mice, and they randomly allocated these mice to two different groups. One that slept in the dark and one that slept with a light on at night. And they measured in grams the amount of weight that these things gained. So you have here the data, the amount of weight gained by the mice that slept with the light, and the amount of weight gained with the mice that slept in the dark. And just kind of a quick look at the data seems to indicate some of the heavier weight gains were in this group here. Well, let's actually try and figure things out and look at the data to see what kind of results we would get if these things were just by chance. Now, I gave you a link that I put in the chat that opens up to this page, and we got this data. In fact, over here, you can kind of see the different data sets. You have the people or the mice that slept in the dark, their data values, and the mice that slept in the light and their data values. Now, what would be an indication that there was a difference between these two groups? How would you compare them to decide, yeah, it made a difference to sleep in the light versus sleep in the dark? Or would you just say, okay, well, some of the numbers look the same, so that's it?
I would do a hypothesis test.
Yeah. Go ahead. Two means? Yeah. Thank you, Shane. Yeah, you'd probably do a hypothesis test comparing the two means. And if you look at the two means, if we calculated the difference of those two means, the light minus the dark, we see that on average, these two groups differ by about 2.62 grams. Is that a lot? Is that a significant amount? Well, I don't know. How likely would that be that if sleeping in the light had no difference, how likely would it be that we could get results like that just by chance? Let's think of it this way. Suppose that these mice were predetermined by some gene to gain that amount of weight, and that it just happened that things were divided up so that the light and the dark samples ended up the way they were to give us our results. But basically, overall, sleeping in the light or dark didn't make a difference. So what I could do would be put all these mice together in one big pool. And then I'll draw out 8 and put them in one group, and the other 10 will be put in the other group. So just take all this data, jumble it up, and resample it. Now, a good question for you, kind of a review question, is how many ways are there to choose 8 samples out of this group of 18? How would you calculate that? Does anyone know? That would be a combination. So it would be 18, go to the math key, over to probabilities. Of course, you can do it on Google Sheets as well. Down to combinations, 18, choose 8. What if you did 18, choose 10? Well, choosing which 10 you want is like choosing which 8 you're going to leave out. So we should get the same value here. And we do. So there's 43,758 different ways you could choose these groups. Let's see how likely it is that if we chose something at random, that we get results that are this extreme. And the cool thing here is that we can generate a random sample. So let's generate a random sample. And here's my random sample. if I just shuffled up all the data and assigned them at random to light and dark groups, this time I get a difference of negative 0.52 grams. Okay, so the group that slept in the dark actually gained more weight than the group that slept in the light. Kind of counterintuitive, and it plotted it for us there. Well, we've got 43,757 more trials to go before we get them all, right? So what I'll do is I'll divide you up into groups and we'll get going. This should take us to the rest of the hour. Okay, I'm kidding. We're going to use technology to do this. If you notice over here, we can generate 10 samples, or even 100 samples, or even how about 1,000 samples? And basically what we want to look at is how common is it to get these kind of results, that you have a difference of 2.262 between the light and the dark in terms of their weight gain. And you're starting to see that here. So we've got all this data. Does it look very common to get something out here around 2.62? Does it happen very often that with this data, you're going to get something that extreme? Well, if you were doing a hypothesis test like this, mu1 equals mu2, what's the alternative hypothesis going to be here?
At least one of those means is different.
At least one of those means is different. Cool. Now, we just got done with analysis of variance, but if you're back in chapter 9, where you had two means independent samples, would the alternative be a left tail, a two tail, or a right tail?
Two tails.
Two tails. So let's click two tails. And it gives you this number, 2.509. So there's a 2.5% chance that you're going to be out here in the right tail if your difference was 2.509. Well, our difference is even farther than that. So tell you what, click on that number and let's type in the 2.62 that we got. What's the chance that you're going to get a value so extreme? Now for me, it's 0.019 in this tail and another 0.019 in this tail. So 0.038 would be the chance that the null hypothesis is true, but I get something this extreme. What kind of values are you getting? Because yours are probably a little bit different than mine. So what kind of values are you getting? Are you able to get these values?
I got 0.025 for each tail.
All right, so you're right exactly at 5%. So basically, when we collect this data, and let's look back at our original data set, we've got a difference of 2.62. You've got one of two options to believe. Either the null hypothesis is true and you just got an unusual value, or the null hypothesis is false. Because it's kind of unlikely that we're going to get something this small and this unusual given given the null hypothesis is true. It's unlikely. For me, it only happens about 3.8% of the time. The 0.019 times 2, because it could happen in either tail for a two-tail test. If it was just a right tail test, then it's just going to be the one. It's just going to be, you know, 0.019. Yesterday when I did this simulation, I got 0.012. So I got a smaller p-value. So in any case, that's what your p-value is. It's the probability that the null hypothesis is true and you get something at least as extreme. And that's what's going on here. We took our original data and just jumbled up and repeated our sampling of this to see what kind of possibilities we could get. And you know, it ends up that you're kind of unlikely to get something this far away from the rest of your distribution if the null hypothesis is true. These are just unusual values. So one of two things has happened. The null hypothesis is false, or if the null hypothesis is true, you got an unusual or unlucky or rare kind of value or distribution of data. And it's up to you to decide. But the p-value is the measure of that. So that's why we use it as our guide to reject the null hypothesis or not, is how big that is. Okay. Any comments or thoughts on that? Any follow-up on that? All right. Well, I hope it helped. Thank you.